Hello friends, welcome to a new video. In this video, we are going to solve three problems to understand the distribution, statistical distribution, namely Maxwell-Boltzman distribution and fermi-dirac distribution, and then finally Bose-Einstein distribution. Before going to the problem, I will just give you a brief introduction to this classification of statistical mechanics. Okay, mainly statistical mechanics is divided into two, which are classical statistics and quantum statistics. Okay, here in classical statistics we have only one class, that is Maxwell-Boltzman distribution. Okay, Maxwell-Boltzman distribution. Okay, here in quantum statistics we have two classes. First one is fermi-dirac distribution. And the second class is Bose-Einstein distribution. Okay. Then a classical particle. Here we deal with classical particles. Okay, here we will deal with classical particle. Classical particles are distinguishable. Okay, so what do you mean by distinguishable? Distinguishable simply means we can distinguish these particles. For example, if say two particles are there in the system, then we can label them A and B. A is first particle and B as second particle. We can label separately A and B. That is meant by distinguishable particles. And the second point is here is that there is no restriction on filling of particle in the same energy level. It means we can, if there is an energy level, we can fill as many as the particle. We can fill as many as particle. This is particle 1, particle 2, particle 3. We can fill n number of particles in the same energy level. That is the most important point in classical statistics or Boltzmann distribution. And then the third point is the number of ways. We have a formula to find the number of ways, which is equal to, we can denote that as Wi. Number of ways is Wi, which is equal to n factorial into Gi all power ni divided by ni factorial. Here capital N is total number of particles, and Gi is state, number of state or substate, number of substates, and small ni is the number of elements or number of particles in eith energy level. Okay, so This is the formula to find number of ways. So just remember this formula, then you can easily solve our problems. Okay, then next we move to fermi-dirac distribution. Okay, in fermi-dirac distribution, this distribution is obeyed by the particles called fermions. So what is fermion? Fermions are identical particles. These particles are identical and half integral spin. They have half integral spin and indistinguishable. We cannot distinguish them. Okay. So, and the next important point is that we can use different color. They obey Pauli's exclusion principle. They obey Pauli exclusion principle, which means no two particles can exist in the same level. No more than one particle cannot exist in same energy level. Okay, there is only one particle in the one energy level. Okay, that is the most important point in the fermi-dirac distribution. And the formula, and finally we write the formula. Okay, wait 1 minute. Okay, the formula for Wi means number of ways, is Gi factorial divided by Ni factorial into Gi minus Ni factorial. Okay, this is a formula to find the number of ways in fermi-dirac distribution. So we need to remember this formula in order to solve the problem very quickly. Okay, we will solve 3 problems related to these formulas. Wait, okay, before going to the problem, I will going to discuss Bose-Einstein distribution also. So let's do it. Okay, this type of distribution is obeyed by the particles called bosons. Boson, these particles also identical particles, means they are indistinguishable. We cannot distinguish. And then they are integral spin. Fermions are half integral spin, whereas fermions are half integral spin, whereas Bose-Einstein distribution or bosons are integral spins. Okay, that is one of the difference between bosons and fermions. And then in case of boson, we can put any number of particles in the same energy level, but there we need to consider the constraints. We can put more than one particle in same energy level, but we need to consider the constraint according to constraints. Constraints means, I mean, if they are saying total energy is this much, then you should fill the particles according to that constraint. Okay, that is mean by constraint here, nothing more than that. Okay, next our task is write the formula. Okay, the formula is Wi is equal to Ni plus Gi minus 1 all factorial, there is minus 1, and divided by Ni factorial into Gi minus 1 factorial. So this is a formula. Okay, this is the formula. So we are done with all this. This is for Maxwell Boltzman distribution, and this is for fermi-dirac, and this one is for Bose Einstein distribution. Okay, so if you want, pause the video and let's write these points in a paper so that it will help you in future. Okay, so now next we are directly going to the problems. So the first question is this one. Okay, a Maxwell-Boltzmann gas has two particles. There are two particles in ith state whose degeneracy is 3. So there are two particles, so we are going to solve this. There are two particles, and here it is given degeneracy is 3, so G is 3, and Ni is 2, or total number of particles also 2, n equal to 2. Find out number of independent ways selecting the particle in this state. Okay, there are two methods to solve this problem. First method is directly use the formula and find out the answer, and the second method is table method. Okay, first we are going to use the table method. Okay, in order to do that, we label the particles. Here we deals with Maxwell-Boltzmann distribution, means the particles are classical particles, so we can label them A and B. These are the two particles, and here it is given there are 3 states, so state 1, state 2, and state 3, and here ways. Okay, so we make a table. Okay, the first way is this one. Okay, first way, A is here and B also here, and the second way is A and B are in the state 2, and the third way is A and B are in state 3. So this is state way 2, and this is way 3. Okay, and then A is here, B is here. This is state 4, way number 4, and then A is here, B is here. This is way number 5, and then A is here and B is here. This is way number 6, and then B is here, A is here. This is way number 7, and then B is here, A is here. This is way number 8, and then last way is 9, which is how? Let's think. B is here, B is here, and A is here. Yes, we're done. Okay, these are the 9 ways to select the particle or to distribute the particle among 3 sublevels. Okay, then next way, this is method 1 or method 2. Let's say this is method 2. And what is the method 1? Method 1, which is very easy. Easy method is method 1, which is use the formula. Okay, use the formula. We know the formula. Wi equal to, what is the formula? Wi equal to n factorial into gi all power ni divided by ni factorial. See here, this formula. Okay, now put values, which is capital N is 2, so 2 factorial into g is 3 power 2 divided by 2 factorial. Okay, so this 2 factorial and this 2 factorial will cancel, and then 3 square is, what's 3 square? 9. Very easy. Okay, clear? I did this table method in order to understand the concept. If you want only answer, if this question is asked in the exam, then I prefer method 1. Then why we use method 2? Now, in order to understand the concept, we use the method 2. Method 1 is very easy. So we move to second question. Second question is exactly same to first question, but the only difference is that instead of Maxwell Boltzman gas, here we have fermi-dirac gas. So the solution will change. Okay, we can solve this problem. Okay, here we have fermi-dirac gas. So here also 3 particles. So Ni is 3 and degeneracy is 3. So G is 3, and fermions. So they are indistinguishable. So we can't distinguish. So we label A. This is mean by indistinguishable. We cannot label as A and B because we don't know. We can distinguish them. Okay. So first we do this problem by method 2, which is table method I call. Okay. So ways: state 1, state 2, state 3. Okay. So draw a table, and the first way is, here also we need to consider Pauli's exclusion principle because we deal with fermions, so we need to consider also Pauli's exclusion principle. It says we can't accommodate more than one particle in the same state. Okay, then the first way is A is here, and then second A is here, and the second way is A is here and A is here, and the third way is A is here and A is here. Okay, these are the possible 3 ways. So we have total 3 ways. So answer is 3 way. How to do this with formula? Okay, we will do that also. Method 1 is just use formula. Okay, what is the formula? Wi is equal to, remember the formula which is important, gi factorial into ni factorial into gi minus ni factorial. Okay, let's see. Yes, formula is correct. Gi factorial divided by ni factorial into gi minus ni factorial. So we move to our question. Yes, so put the values. Gi is 3 factorial divided by ni is 2 factorial, gi 3 minus 2 factorial. So it becomes 3 factorial. We can write 2 factorial into 3, and here 2 factorial, here 1 factorial is 1. So this 2 factorial and this 2 factorial will cancel, and finally we get the answer 3. Here also we got the same answer 3. So we done this problem, and then we will move to third problem. The problem is same, exactly same, but there is a small change because here we have Bose Einstein gas. Okay, so here also we are going to solve this problem. So boson, so particular indistinguishable, indistinguishable. So we label particle A and A. We can't write A, B because here the particle are indistinguishable. And here we cannot, we no need of considering Pauli's exclusion principle. So no Pauli exclusion principle, because these are bosons, so no need to consider Pauli's exclusion principle. We can accommodate more than one particle in the same state. The only difference from Maxwell Boltzman is here the particles are indistinguishable. So we first we do with method 2, which is table method. So we write the table ways state 1, state 2, state 3. Okay, let's ready. So first way is A is here and the second A also here, and the second way is first A is here, second A also here, and the third way is A. This is third way, and the fourth way is first A is in the state 1 and the second A is in the state 2, and the fifth way is A and here in third state, and the sixth way is first A in the second state and then second A is in the third state. So 6 ways, 1 2 3 4 5 6. Okay, 6 ways. This is the answer. We have 6 ways. So we will do this same problem with a formula. This is we call method 1. Use formula. The formula is Wi is equal to Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. So Ni is 2 plus 3 minus 1 factorial divided by Ni is 2 factorial, Gi is 3 minus 1 factorial, which is equal to 2 plus 3 5 minus 1 is 4. So we write 4 factorial divided by 2 factorial into 2 factorial. So 4 factorial we can write 4 factorial as 2 factorial into 3 into 4. Here 2 factorial into 2 factorial is 2. So this 2 factorial and this 2 factorial will cancel, and this 2 and this 4 will cancel, and remaining 2 will be there. 2 into 3 is 6. So we got 6 ways. Same answer we got. Here also we got 6 ways. Okay, so we done with this. So I hope it is clear. We learned about Maxwell Boltzmann distribution and then we learned about fermi-dirac distribution, and then third we learned about Bose-Einstein distribution. Also we solved one problem, three problems in order to understand this concept very clearly. So I hope this video will help you. If you have any doubt, then please ask in the comment section. Also share this video to your friends. They are preparing for IIT JAM, GATE, etc. Also BSc MSc students. And please subscribe this channel and like this video. Thank you.